Hello, everyone. All right, welcome to our last lecture. All right, and just want to say hi one more time, and just want to close our course with the topics that we have left, which is about circuits analysis. Okay, so what I'm going to do right away is just to show you one more time about how to apply the Kirchhoff's rules. Okay, and I think you already have seen from last time that it's not that bad. And in terms of the recipe that we built, which is based on how you calculate the potential difference when you go around any closed loop. And then you say that because of the path independent of the potential, it means once you complete the whole loop, then the potential difference that you collected across, for the whole path that you travel around that loop must add up to zero. Okay, so that was the loop rule of the Kirchhoff's rules. And there's another rule in Kirchhoff's rule saying that it's a junction rule, which is just came from the conservation of charge or current. So it means the current that's flowing in must be equal to the current that is flowing out. I'm just talking in the air right now. So that's what it is. Okay. So on the left, that is the one that talking about the junction rule. The sum of the current flowing into a junction must be equal to the outward going currents. And on the right, that is the loop rule. The sum of the delta V across any closed loop must be zero. Cool? All right. So what we are going to do today is just to redo it one more time, just to confirm that you guys know how it's done. And in this example, as you can see that if you look at the circuit given here, there's no current given anymore. And we have already said that it's up to you. Because you don't know it, you just assumed it. You just assume that there is some current flow in. You just pick the direction, okay? And the final answers that you got, that you will get from the system of equations will reveal the actual directions of the current flow. Okay, so let's dive into it, shall we? Okay, so the way that we do this is just once again, you recognize that this is a kind of circuit that cannot be simplified any further. So as you can see that, you cannot find any equivalent resistance anymore in this circuit. So there's no way else that you can do. This is pretty much the simplest that it's going to get. So just simply applying Ohm's law is not enough. So we are going to try using the Kirchhoff's rule. Okay. So what we did last time was we just identify a single line wire. It means that you just pick the line, the wire that doesn't have any branches. So once again, when I see this, I see, okay, the left side of this one, that is a single wire. Okay, so definitely along this yellow wire, there must be only single value of a current flowing through it. And the second one that I can identify is just the middle one that highlighted in blue. And the third one that I can see is the one on the right. Okay, so with that, now we are going to assign the currents flow in each wire. And you can pick any direction that you want. For example, I can do current along the yellow wire to be I1 flowing upward. And I can assume that there is an I2 flowing upward in the blue wire as well. That is fine. And I can also say that there is an upward flow of the current I3 along the green wire. I don't care. Okay, so by assigning all the currents like this, now you can see that there are two junctions, junction A and junction B. You can pick any junction you like. For example, if you're looking at junction A, so at A, what you get is all the current in must be equal to current out. You look at this one, the current I1, I2, and I3 are pointing towards point A. So that's the inward current. So I can say I1 plus I2 plus I3 is going to be equal to current going outward. None. That's it, guys. That's my first equation. Done. Sounds good?
Okay.
And as you can expect, if you assume all the currents flowing into that junction A, you're going to be definitely get some of these i's to be a negative number, right? So the only way that you can have three numbers add up to zero, that's mean among them, there must be some negative numbers. And so there must be some direction of the current that you assumed here is going to be opposite to the actual current that you are going to get out of the system of equation that we are about to build right now. Cool? All right, then keep going. So now that's done for the junction rule. If you notice, if you want to try to apply the junction rule at junction B, you get exactly the same equation because at B, all of these currents, I1, I2, and I3 are pointing outward. So you get the same equation, I1 plus I2 plus I3 equal to 0. No big deal, okay?
Okay.
All right, now what else that we can do? Next step, we're going to apply loop rule. So you just have to pick a loop out of a few loops that you can see in here. So what we can do is just pick a loop. So let me assign the corner some names here. OP. All right. So now pick any loop you like. For example, you might want to take like, okay, I'm just going to take the outer loop. So let's take a look at the loop M A N O B P M. You see that? So I'm picking the outer loop and I'm picking in the clockwise direction.
Okay.
Okay. So I'm going to go clockwise along this loop. So I hope you're seeing this. So let me highlight briefly. So this is the loop that I'm talking about. I'm going to go like this. Cool. All right. So let's try that one. So let's go through this one together, shall we? All right. So I'm starting from point M. So I'm just going to walk down this wire. Now I'm hitting R1. And as you can see, R1 has I1 going through it. However, because I'm walking in the same direction as my current flow I1, so it means I'm going toward a lower potential. So that means the potential difference is going to be negative. So it's going to be negative I1 R1. Cool? All right, keep going. Nothing is nothing. Now I'm hitting R1 again, but now the second R1 that I have has an I3 going through it. So because now you're going against the current, so it means you're going toward a higher potential. So it means the potential difference will be positive, you're going higher, and it's going to be I3 R1. Cool? Keep going. Nothing end, turn. Now you're hitting the positive terminal of the battery. So that means you're trying to going through from the positive terminal to the negative terminal. So that means you are going toward a lower potential. How much? E3. So we have negative E3 potential difference across. Cool. Keep going. Now you're hitting another R1 down here. And once again, you're going against I3. So that means potential across R1 is going to be negative I3 R1. Keep going. Now point O. So keep going. Nothing. At B now. Nothing. Now you're hitting R1 again. But now R1 having the currents I1 going through, and then you are going along the currents flow. So it means you are going toward a lower potential. So the potential difference is going to be negative I1 R1. So guys, so good. So first good. Yeah. Keep going. Now you are at point P. Turn. Nothing. Now you're hitting the negative terminal of the battery. So you are going from negative to positive terminal. You're going uphill. You're going to a higher potential. So it's going to be positive change. How much? Of course, it's E1. And now you are down here, nothing more. Now you arrive back at point M. Complete the whole loop. So once your loop is already closed, the sum that you have already picked up must be added up to 0. And you are done.
Okay.
That's your equation number 2. Cool. See, it's not too bad. All right. And now you just have to pick another loop because you have 3 unknowns. You want 3 equations. So with that, now let's pick another one, shall we? All right. So I'm going to pick maybe the left loop and I'm going to go counterclockwise this time. Just change the style a little bit. So you are going counterclockwise on the left hand loop over here. So that means I'm looking at loop. Let me start from A, M, P, B, A. Cool. That's the left hand loop there. So that means I'm going to start from point A here, the blue dot. Now start analyzing counterclockwise. Now I'm hitting R1 with the I1 going against me. So that means I'm going toward a higher potential. So the potential difference across R1 is going to be positive I1 R1. Now I'm here at point M, nothing, turn, coming down here, hitting the positive terminal toward the negative terminal. I'm going to a lower potential. I'm going downhill. So that means it's going to be negative E1. Keep going, hitting point P, nothing, turn. I'm hitting R1 with the I1 going against me. So I'm going uphill, higher potential, positive I1, R1. Keep going. Now nothing. Now I'm arrived at B, turn. Hitting the negative ends of the E2, going to positive ends. I'm going higher, uphill, plus E2. Keep going. Hitting the R2 with the I2 going through because I'm following the current I2. So I'm going toward a lower potential. I'm going downhill. So the change is going to be negative I2 R2. Now I'm arrived back at A. Complete the whole loop. This sum must give you 0. This is your third equation.
Okay.
Cool? And that's it, guys. So solve these three equations for the I1, I2, and I3. Once you have those, that's it. You are done. I1 equal to what? I2 equal to what? And I3 equal to what? And you can expect one or some of these i's must be 0 for sure. Okay. Sounds reasonable, I think. Okay. So by showing you this, I think this is very good exercise for you to try, and it's pretty much like a guarantee that you should be able to execute this kind of like, you know, the way to solve this multi-loop circuits for sure in the exam. All right, not a problem at all. Okay, any questions? If you have, then well, we'll have a chance to chit chat a little bit before the exam. Yeah.
Okay.
All right, guys. So I hope this works. All right, and this pretty much review what we did last time. Okay, that's cool. So I have one more. So this one, I think this is a nice DIY, but it's kind of like you're going to repeat this over and over again because, I mean, as long as you have like, I can say this, you can call this like a 2 loops, even though the actual one you can pick like 3 kind of loops here, but you can see that there are 2 loops connected. So as long as you have only these 2 loops, then you are going to have like 3 unknowns in your equation. So you're going to end up with just only writing down 3 equations. The only complication will come in if you have more loops than just 2 loops connected. All right, but it depends on the number of wire that can sort of like compose the loop. So the amount of unknowns depend on the amount of a single wire in your system. With me? All right. So as you can see here, I can say, okay, this is my 1 wire, 1 single value of the current flow through. The other wire is in blue here, and the other wire is in green. So as long as you can highlight these 3 colors like this, definitely you're going to need 3 equations and you're done. All right. And I think in our exam, I'm not going to go beyond this because by having like higher loops circuits, it's only introduced complexity in system of equations. But in terms of physics, it's pretty much the same thing. You just apply either junction rule or loop rule. You just have more stuff to do, right? But the concept is just that. Kirchhoff's rule is just only those 2 rules that you really need to understand. Sounds cool? All right. So I told you the last one is going to be easy.
Okay.
It's like cool down. Sound like, okay, we just like, you know, farewell lecture. So just keep it like, you know, toned down a little bit. Don't go crazy. All right. All right, guys. So the last stuff that I'm going to talk to you about is now we're going to combine the capacitors that we learned. All right. We sort of knew the property of capacitors. We know what's happening when you squeeze in dielectric material in between. You can increase the capacitance by kappa times, right? And the kappa is the dielectric constant. So that's easy. And then you learn that the kappa is just a factor that you can turn the epsilon naught, which is just a vacuum, into the epsilon of that material, right? So that's easy. So what we have over here is just now, you already got everything sort of like analyzed here. But the only device or the only components that you have on here is just resistor. Okay, and of course you have source in there that you can think of it like a battery. However, what we are going to learn this time, now we're going to incorporate capacitor into our circuit, and we would just want to know what's happening here. So the symbol for the capacitor is just to reflect the nature of the parallel plates. So you're going to have two straight lines parallel with equal length like this. So this is a symbol representing a capacitor. Cool. All right. Now, keep in mind that the capacitor is just a parallel plate. And if you don't do anything to it, it's just going to be a neutral plate, conducting plate. So this is what happened. This is the easiest type of the circuits that you can build having a capacitor within. You have a source and you have that capacitor and you're done. That's it. And of course, if you only have this, that's not much to it, because as you can see, the left plate here is connected to the positive terminal of your source. And the right plate over here is connected to the negative ends of your source. So of course, now you know the left plate of the capacitor has higher potential than the right plate. So no doubt, then you're going to accumulate the positive charge on the left and you're going to get negative charge on the right. And that's it. That's not much to it. And because if you remember the formula, the capacitance is just a ratio between the charge over the potential difference across. And now you can see that you apply this much potential across. You guys with me? All right. And don't forget, whenever you see V, that is the same as a delta V, and it's going to be the same as E. Depends on what kind of terminology you want to use, but they are meaning pretty much the same thing. So over here, what you have over here is means like you applying the potential of E or the delta V or the V across your capacitors, having the capacitance C. So actually you can calculate the amount of charge that's supposed to be on that as simply C times E. And that's it, you're done.
Okay.
Simple enough, yeah? So that means that's the whole thing. If you know the potential across the capacitor, and somehow you know the C of that capacitor, so you should be able to calculate the amount of charge on that capacitor using this expression right there. Okay, so it seems like, well, the potential difference across seems to be the one that seems to be very useful. Because once you combine the delta V with the known value of the capacitance, you are able to calculate the amount of charge that's supposed to be deposited on those plates. Cool? All right, and don't forget, one plate is supposed to be positive Q, the other plate has to be the negative of that Q. All right, now, this is not super interesting because that's it, guys. It's just like, okay, we just introduce potential difference across two plates. What's more interesting is this. Now we're going to have both in our circuits. Here we go. See? So now you have resistor R and you have capacitance C. And now you have a source E ready. But right now, because you want to start everything from time 0, so you can call this one like, okay, T equal to 0 setting. And at that point, the switch is open. See that? So right now, everything is like neutral. There's nothing in here. What is happening is once you close that switch, bam, you kind of know, Ajahn, once you close that switch down, you complete the circuits. And hence, that's why they call name circuits. You want to complete circuits. All right, but anyway, the point is once you close down the switch, now things is ready. Okay, so the charge now ready to flow. And you can expect, because you have positive ends of the source on the left and the negative ends of the source on the right. So you're supposed to, like, I can guess that the current's supposed to flow clockwise. But I just want to know how much. And I just want to know what is sort of like, is there anything else related to this whole business over here? How can we deal with this kind of thing? Let's give it a shot, shall we? And this is going to give you the last blow of your brain a little bit before we sort of like finish this course right here. So what I'm going to do is this. We call this time 0, we want to know what's happening to this circuit at any time t. Okay, and the way that we can analyze this one is, once again, we're going to apply Kirchhoff's rule, guys. This is what is happening. Here we go. So what we're going to do is we're going to apply Kirchhoff's rule and just have fun with it. So we're just gonna start from the upper left corner. Here we go. And then we're gonna go around in circle like this. You can call this like A, B, C, D, A. Cool. All right. So what we have over here is, let's try for fun. So what you have over here is, you go from A, keep walking. Now, because you assume that the current is flowing in the clockwise direction, even though you said you don't know what actually is supposed to be, but you assume it's supposed to be in that direction, that is fine. So what you have here is, you just start from A. So let me write like this. So the loop A, B, C, D, A. Okay, start, walk. Now you're hitting the R with the current I flowing through. So the potential difference across is going to be IR. Does that make sense? But because now you're walking in the same direction as the current, you're going toward the lower potential. So it's going to be negative IR. Keep going. Now at B, turn, nothing. Now at C, nothing. Going through switch, nothing. Now you're hitting the negative terminal of your source. And now you jump, going from negative to positive terminal, you're going uphill. So the potential difference is going to be positive. E, keep going. Nothing happened. Now, what do you think it will happen to the capacitor? Well, Ajahn, of course, the capacitor must have potential across it as well. So what I can do is I can say that it must be some potential difference across this capacitor, right? However, we already learned that the C equal to Q over V, or that means V is just Q over C. Cool. All right. So that means if you somehow know the charge in the capacitor, you are able to calculate the potential across. It's going to be the ratio between Q over C. However, now imagine this, when you put the bottom plate, and as you can see, the bottom plate is connected to the positive ends of this source. So that means you pretty much sure this thing is going to turn positive and the upper plate is going to turn negative. So you have the lower plate to be like a positive charge and the upper plate is to be negatively charged. Now you're walking from below. It's like you're hitting a source, or I mean, that doesn't need to be a source, but you imagine that you're going from higher plates to the lower plate. So it means you're going downhill, you're going downward in potential. So that means you're going to have the negative change. And how much? It's going to be this much. So it's going to be Q over C. Cool? All right. Now you keep walking. Now you arrived at A and you're done. The sum must be equal to 0. I can move things around a little bit, whatever, but this equation is exactly this equation. As you can see, you are pretty much done in the first step. Well, here. Sorry. All right, just one star is good. All right, so that is your stars equation that you want to pretty much solve. Now the question is, what do you see here? All right, I think I supposed to use like a mini I over here, okay, because we're going to reserve the capital I to something else. That is fine. Okay, mini I there. Okay, so what are you going to do with this? What do you think? So this is my final gift to you. This is a differential equation, guys.
Okay.
The reason is that because you have the current in this equation and you also have charge on here. You're not going to be able to solve this one easily because charge and current are different things. Okay, this is not just like a simple linear equation for you to solve for anything. However, not only that, I have to say moreover, there is a relationship between I and Q. If you remember the pretty much like the first few pages that we started this handout, here we go. Remember this? We already defined that the current, it turns out to be the flow of the charge per unit time. So that means if you speak in the language of calculus, the current is just the derivative of charge. with respect to time.
Okay.
And that's why this is where the calculus creep into that equation. So that means what I can do here, I need to write that current I to be dq by dt. And that's when you start to get, you get the differential equation. So let me write down one more time here, just so we can go through this one together. So it looked like this: minus dq by dt times r plus e minus q over c equal to 0, something like this. Now, the question is, how are you going to solve for, now, as you can see, the unknown right now is going to be q right here, not the I, but that's all right. If you can solve this q to get to the current I is easy, just differentiate q with respect to time and you're done, right? So now the whole business that we're about to do over here is, how can we solve this one? Can we do it? That's the question. And now you have to go back and think about what you did in calculus, maybe calculus 2, is that right? Or you might have taken like differential equation. I don't know which course you took. But anyway, the point is, this is still all right because it's a first order differential equation. So it means the derivative is only the first order. So you don't have to worry too much. All right. So I'm going to show you how this is done. And the technique that we're going to use is called, well, it's not like a full technique or anything, but what you are going to do is you just do the separation of variable. You just separate the variable that you want to solve into two sides, and then things is about to show up right there. So I'll show you right now. So what are those two variables? Of course, q is one thing, that's one you want to solve, but because the derivative is with respect to time. So these are the two variables, right? You can think of it like q is one variable and t is the other. They are related. So what I can do is I can rearrange this equation, and I'm going to put q on one side and I'm going to put t on the other side. Does that make sense? All right, so let's give it a try and see how it goes here. So what we want to do over here is, I'm just going to take the q on one side. Actually, I'm already writing. It's already written on this slide over here. But I mean, if you want to do it yourself, this is fine. But the way that I can do it like this, you probably can, leave one on one side and the other on the other side. For example, I can move this term to the right-hand side, and you are left with just something like this. E minus q over c equal to dq by dt times r, like this, right? Okay, and now it's just the manipulation. Okay, the only thing is you just want everything on one side and the other thing on the other side. So what I can do is this. I'm just gonna pretty much take whatever that has q on it, leave it on one side. And I'm gonna take whatever that has the t on it onto the other side. So what I'm gonna get it like this. Okay, there are a couple of ways that you can do it, but maybe the most obvious one, just to showcase what I'm talking about, is this. Okay, so I can have common denominator over here. So let me write this one as over c, and then you have epsilon c minus q. Cool. All right, so that means I can move c to the right-hand side. So I'm going to have rc dq over ec minus q. Can you see something here? You can see that now the left side of this whole thing is purely on t, is on time. Here. And the right side of this is purely on q. See that? Isn't that nice? So now it's your turn. That, because now the left-hand side is purely t, the right-hand side is purely q. Now you can integrate on both sides. Yeah. And then you start from where? Of course, because you start your time at 0, you want to go wherever you want at any time t. So you put 0 as your lower limit of integration. You put t as an upper limit of integration. And of course, at the starting point, you can say, well, John, when you start this whole process here, your parallel plate doesn't have any charge accumulated yet. So in terms of q, you start from 0 as well. There's no charge on there. And hopefully by the end of this process, you're going to get some Q on there, and this is going to be Q at time t. See? So your lower limits are associated with each other. So the lower limit in time is at 0. On the right side, it must be the charge at time 0 as well. And the upper limit is the time at t. So of course, on the right hand side, it must reflect the charge at that time t as well. Makes sense, right? And you just do the integral on both sides. Can you do it? All right. So the left hand side is easy. Integral of dt is just t, and you just do it. So, well, I don't have here. Let me squeeze it here. So that's what you have here. This integral give you t, and you have the lower limit and upper limit as that, and that is just t. Cool. The left hand side is no big deal. All right. The right hand side, it's still no big deal because, okay, I don't know, you still remember how, but this integral, I mean, if you prefer, let me follow the red ink over here. You can have RC here. I can extract negative sign out. So it's going to be integral of 1 over q minus EC dq. This one is very doable because you, of course, remember integral of 1 over x minus a dx. You said, Ajahn, it's a log of x minus a with the absolute side, if you like. So this is very doable. And that's why the integral that you get on the right-hand side is going to be negative RC log q minus EC. That's not too bad at all. All right. So that's what we get over there. And you just take the limit from the lower to the upper to be 0 to q at time t. Cool? All right.
Okay.
And now, almost done, guys. Once we plug in, so let me expand this one out. Negative RC is still there. You put the upper limit in there. It's going to be log epsilon c minus q. Subtract log of, not epsilon, sorry, EC minus 0. Here we go. All right. And log, the difference of log is just the log of the ratio. So that's why you get the next line over here. Cool. So there's a log EC minus Q divided by just EC alone. And because you really want the Q to get extracted out. So what are you going to do is just, this is mathematical manipulation a little bit. So you can move negative RC to the left-hand side, do the inverse logarithm a little bit, and do the arrangement. So this is your stuff. I mean, you have to practice this one at home, but at the end, you should get this equation right here, and you are done.
Okay.
Is it okay? So what you're getting over here from this Kirchhoff's rule lead you to differential equation first order, and you apply whatever you learn from calculus, solving the first order equation by just variable separations. You put t on one side, put q on the other side, and you integrate on both sides. Allow you to figure out what should be the q, the charge at any time t. And this is what you get. You get the change of the charge inside the capacitor as a function of time.
Okay.
And if you only want the current, we already told you that if you want the current is just the derivative of q with respect to time. So you just differentiate that once. Of course, that CE will disappear because, I mean, not the whole CE, but I mean, the first term will disappear because it's just a constant. So once you differentiate, you're going to get this second star's equation here. And you know, differentiate exponential, you get exponential function again. Cool? So that's nice. So you already solved both what should be the charge on the capacitor and the current on the capacitor as a function of time. And as you can see, it has an exponential built into it. Okay. Now here comes the question. Staring at this, guys. Have you seen this type of equation before?
No.
Think carefully. Have you seen this type of equations before? It looks complicated at first, but if you look carefully, what kind of shape of this equation should be? What do you think? Think about it. All right. It's almost done, guys. If you unlock this whole characteristic of this equation, and then you are pretty much done here. So what I'm going to show you is this. Just discuss this a little bit and see how it goes. So the equation, it has a shape of this. So first of all, you guys familiar with e to the negative x? Cool. So for this, that's common. So what you have over here is just an exponential decay. Cool. This is e to the negative x, right? And everyone knows that it's going to intercept the y-axis at 0, 1 right there. That's the exponential decay. But then what you saw before is that there's a 1 minus. So that means you have to put the minus sign into it, minus e to the negative x. What is a minus e to the negative x? You just flip this over down here. Whatever you saw, you just flip it down to the negative side. So it's just a mirror image around the x-axis. So that means it's going to hit the y-axis at -1 instead. Almost. And then you just plus 1 to it. When you add 1 to it, what does it mean by adding 1? You just lift the whole green function here up by 1. So it means what you do is just you lift this whole thing up by 1. Lift it up by 1. So from -1, you're going to hit at 0, 0 right there. Cool. All right. And now this is the characteristic of the function that we want. The shape of that 1 minus e to the negative x is this dude right here. Here we go. I don't know. Can you see this? And we're going to start everything from 0 because we don't care about the negative time. So it means this is a very well-known behavior. It's an exponential in nature, but it's an increasing function starting from 0, 0. And that's why you should be able to understand this curve right here. So this curve starts from 0, 0, and it's going up, 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 and it's curved up like this. Cool. All right, this is not bad. All right, now there are a couple of things that you should know from this one. Here we go. Because it's curved up like this, it's going to curve up, 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 but eventually it's going to pretty much like it doesn't want to go up anymore. So it seems like there is some sort of like a asymptotic behavior. You remember this word? It's like this line is supposed to approach some value if you take time and let it ride for a very long time. So this is times axis down here. So that means what I want to show you is this. What happened when time approaching infinity? Q as t approaching infinity. What do you think it's supposed to be, guys? I don't need this. What do you think? Well, John, once time is super, super, super big, this term right here, this dude here, this is, yeah, here, this whole thing, is an exponential to the negative infinite. And that means it's going to diminish to 0. Gone. It's going to be gone. So this term eventually is going to disappear as t approaching infinity. Does that make sense? So that means what you can see is at time to be very, very, when time is so big, the Q, the charge, is approaching CE times 1. So it's just CE. Whew. So you can say this is your Q max.
Okay.
So that is your maximum charge that you are going to eventually get. And that is right here. See, that is your asymptotic. Yeah. Asymptotic value. This curve right here is approaching CE. So your C times E is supposed to be the highest charge that the capacitor is going to get. But you have to wait. You're not going to get things charged up right away. It takes time. How long? That's the question. How long does it take for you to charge up? Here comes the next question. You come down here, now you start to understand the behavior of this one is increasing exponentially, right? But then you think about this. When you notice this one, this is not just like e to the negative t. It has the factor RC built into it. So before we get anywhere further than this, what should be the unit of RC? That is the first question. You probably had enough of this. What should be the unit of RC? So once again, I think I talked about this a couple of times. It's an exponential to the negative t over RC. Anything follow exponential function, trigonometric function, logarithmic function must have no units. You never had like units of e to the kilogram. That doesn't make sense, right? Or you don't have like sine of Newton. That doesn't make sense. So whenever you have any parameters, any quantities that follows exponential, sine, cosine, logarithmic function, whatever things that follow must have no unit. It's dimensionless quantity. Because now you already knew that this is in second. So that means the RC over here must be the unit of second as well. So isn't that cool? Your resistance R multiplied by the farad of the capacitance give you time.
Okay.
RC give you time. Okay. So with this sort of like the config, the form of the function, it looks like this, right? So now let me ask you this: if you have two curves, the green curve and the red curve, like this, right? So you can say the green one move up quickly, the red one move up more slowly. So if I have 1 minus e to the negative t over 10, and I have 1 minus e to the negative t over 100, do you think which one's supposed to be the green and which one's supposed to be the red? What do you think? Okay, enough. What should be the red? Which one should be the green? So now you see that, Adan, we just talked about it. That 10 must be the unit of time. So now you know 10 give you something about time, right? But now because one thing is 10, the other one is 100. So which one should be the one that actually move up quickly, more quickly than the other? So the way that I might be able to check, it's pretty simple. So what I'm going to do is this. Well, hey, Dan, let me draw a line here at the height of 1 minus e to the negative 1. Does that make sense? Is that easy? Just say, hey, comparing these two functions, which one's supposed to hit the value of the function of 1 minus e to the negative 1 first? What do you think? Well, Ajahn, of course, the one on the left, it takes only 10 seconds to hit this value. But the one on the right, it takes 100 seconds. So that's what I'm saying is the green one, it takes only 10 seconds to hit that level. But for the other one, it's going to take longer time. And that's to be expected that this supposed to be the red function and this supposed to be the green function. Now you see what is the role of the number that is dividing the time. It tells you how fast this exponential growth is growing. Isn't that cool?
Okay.
One more time. Come back here. See? The RC is dividing the time. So if you have RC very small, it means it takes a small amount of time for this function to grow. If the RC is big, like 100, it's going to grow slowly. That's why we're going to name this RC to be time constant, because it's a number that defines how fast your function is growing. That is the characteristic of this pretty much. I think this equation shows up everywhere in mathematics and physics and all branches of science. That's for sure.
Okay.
Okay. And I hope by learning this, you understand how to interpret when you have the exponential function with the time and you have something divided by it, you know that, oh, that thing that show up underneath must sharing the same unit as time. So now you know RC to give you time. And we can call that some constant of that circuit. So sometimes you represent this one as a tau. That's a time constant. So by introducing that one, it's kind of nice in the sense that if I say, hey, instead of say, I want to wait and see what is the behavior of this circuit at time of 10 seconds, I can say what happened at one time constant. Does that make sense to you? So if I say one time constant, so it means I want to know Q at 1 tau, you know right away, what do you need is going to be the constant C times E is in the front. It's going to be 1 minus E to the negative 1 all the time.
Okay.
If I want to see what happened at 2 time constant, you know right away it's going to be 1 minus E to the negative 2, regardless of the RC value. So we can speak about the same value all the time. Yeah, monitor is not freezing. I'm just give you some time to absorb this whole thing right here. Cool. So think of the time constant is just like you buying a donut. If you buy one piece of donuts, that is fine. But if you want to buy 12 pieces, you say, I want a dozen of donuts. So 1 dozen mean 12. Same thing over here. Instead of talking about, hey, I want to see what is going on at time 5 seconds. No, I want to see what happened at 1 time constant. That is just the unit conversion right there. Does that make sense to you? Okay. All right. So the key stuff that I'm talking right now is just have you to understand that this is the result from Kirchhoff rule first, but the Kirchhoff rule with the capacitance in it, capacitor in it, give you both I current and Q in your equation. So when you both have both of these two are related through differentiation, and that's why you are ended up with a differential equation to solve. To solve that one, you need a little bit of trick in terms of doing some integration. But once you have that, the results give you the exponential behavior. For the charge, it's growing exponentially. And you hit the maximum value right here of CE. Okay. And if you want the current, you just differentiate this one once. And I hope now you understand what is going to be the character of the currents. Can you read this one now? It's going to be easier because you don't have any constant adding to this. It's just exponential decay. How fast does it decay? Oh, Adan, I got it. See?
Okay.
It's the same factor, RC. So RC will tell you how fast or how slowly this current is going to change with time. But one thing that you know, at time 0, you start with E over R because you just plug in T equal to 0 in this equation and you're done. And what about if you wait very, very long? But John, this is exponential decay. So you are going to get 0 at the end. So now let's recap what is happening in this circuit. Here, come back here again, one more time. You start at 0 charge. You close down the switch, bam. The charge start to build up inside your capacitor, right? So this equation showing you that it start to build up from 0 right here, and it's going to get bigger and bigger charge. So I mean, charge start to flow into the capacitor more and more, but it's getting into the capacitor at the slower rate as time goes by. It's getting harder and harder to enter the capacitor. It's getting harder and get harder. Eventually, if you wait infinitely long, there will be no more charge flowing into the capacitor. That means we can say the capacitor is fully charged. And at that value, the maximum charge that you're going to get inside your capacitor is just CE. You're done.
Okay.
And think about in terms of the currents. At first, the charge can just flow into the capacitor, like, go all in. Like, no, the capacitor is free I mean, there's nothing inside the capacitor. It's just like a blank room. So that means the current is going to be maximum right away once you close down the switch. Now you imagine that if your classroom is once again your conducting plate of the capacitor, and if somehow you are the first electron that gets, well, yeah, let's use electron, that's right? So if you are the first charge that gets into that room, you feel nothing. It's like, oh, I'm free. I'm the first one in this room. So that means you can flow in without any resistance or without anything. It's free. So that's why the current is supposed to be highest for the first group of charge that start to enter the capacitor. Does that make sense? But now, because of the Coulomb repulsion, if the next charge wants to get into the room, it will feel a little bit of repulsive force because there already some charge in the room. So it's gonna, push you back a little, but it's still fine. You still have plenty of the room. So the second one still be able to get in, but it's getting a little bit harder. So that's why the current start to drop a little bit. Now more charge start to enter the room. The later charge will get harder and harder to get into the room because now there are so many charges already inside the room. You get pushed back more and more. So that's why the current will die down over time. And eventually, when you're already fully charged, so it means the room is already full with the charge, there will be no more new charge can enter the room anymore. And that's when the current go to zero, when T is long enough and you are done.
Okay.
I hope you understand this whole thing. And this is the beauty of having calculus in your hands, and then you know how to solve differential equation, and you combine that with the exponential function behavior that you probably have learned from, high school mathematics. And then it makes perfect sense when you think intuitively. Yeah, charge accumulation is have to slowly accumulate, but now you already know in detail that the behavior that is accumulating the charge on the plate is exponential. Same thing with the current. The current is going to start big and it's going to die down over time because charge is accumulated more and more inside the conducting plate. And now you know the behavior of that dying down is also exponential. And the factor that governs how fast or how slowly the charge or the current is about to change is just that, bam, RC right there, your time constant, and you are done.
Okay.
So the good thing about this one is, if you look at this equation as like a general form, the good thing is this kind of equation shows up in so many places in science. It doesn't have to be like a RC circuits like this. It shows up in kinetic of maybe drug delivery in your body, the way that the like a nuclear dissociation or the nuclear radiation, or the population change, the maybe economists doing this to calculate the change of the fund flow, or I don't know, there's so many things. As long as you try to relate the value that are linked together through the first order derivatives, you pretty much going to end up with exponential a lot of time. That's my point. Okay, so that's what it is. So I hope you learned something here, I guess. All right, and with that in mind, the reverse process, I would like to show you this. I don't want to sort of like take you through any troubles anymore. If I'm asking you simply and you just answer me intuitively, once you fully charge your capacitor like this, all right, let's say it is already filled, maximum charge, and now you want to discharge it. So you want to let it go. Bam, you just release everything and turn everything into neutral state. What will happen? What do you think? Can you guess? If the charge starting from the max, right? This is the maximum value, and you want to discharge it. Do you think what kind of behavior of the charge is about to come out of your conducting plates? I don't have to draw any new differential equation, actually. I can tell you right away here. You guys with me?
Okay.
Exponential. And this is how simple it is. You're still working under first order differential equation. So you can guess. If you talk about the charge is going to decay over time for sure because you discharge, but you can guess, educated guess that the way that the charge is going to discharge is going to follow exponential decay. How fast is determined by the RC as well. Same thing with the current. You just differentiate this one once. To get to this, you do dq by dt. But once again, see, now you understand why derivative of exponential stays exponential. Because you can also guess that the current will die away with the same factor. This is going to be exponential decay as well. How fast is determined by the time constant. So that's why the time constant is so important here, because it's the factor that determines the rate of the change that is happening in the circuit. All right. And the behavior that we're talking about is the exponential in nature. And you are done.
Okay.
Okay. So I hope you learned something here, guys. And this is what I really want to sort of like give you for the last stuff that I want to talk about. Is just, well, close the whole course with differential equation inside your circuit analysis. All right. So let's do a couple of exercises, and then I think we can consider complete our course here. All right. Unfortunately, we cannot do magnetic. All right. But anyway. All right. This is already a lot. Yeah. Okay. So the maximum charge on a capacitor is given to be EC. How long does it take to charge an empty capacitor to half of its maximum value? See? So you just pretty much forget your differential equation. You don't need it anymore, because all my points that I sort of like talked about were just showing you that the solution from that differential equation give you exponential behavior, and all you need is just take that exponential behavior and then use it. See how it goes. The capacitor is connected in series with a resistor. So that is our simple RC circuit right there. So what I'm saying is, now you know the charge at any time is just the CE, that's your maximum charge, 1 minus e to the negative t over RC. See, that is your main structure of this whole expression right here. But they want to know, how long does it take to charge an empty, that's our condition, we start from empty capacitor, to half the maximum. That half of the maximum is just EC over 2. See? Cool. And now you even know that this is going to cancel. And all right, and let me go through this one with you guys here. 1/2 equal to 1 minus e to the negative t over RC. You flip-flop things a little bit, move things around. So e to the negative t over RC is 1/2. Cool. So take log on both sides. So negative t over RC is log 1/2. But log of 1/2 is negative log 2. That's cool. Start to look familiar, I guess. And then now your t is just RC log 2. And you are done.
Okay.
Probably sort of like remember this kind of thing. You have seen a log 2 RC somewhere. If you still remember radioactivity, half-life calculation. So the log 2 is about like maybe 0.693 or whatever. But the key is, this is how you calculate things at any time. Or if you want to know time, you want to calculate charge at any time, that's fine. But the expression is right here. See, I don't need to get back to the differential equation anymore, because I already good. I know the behavior is supposed to be exponential. Okay?
Okay.
Try again. That's how things are very easy now. So consider a capacitor of capacitance C is being discharged, this is fine, through a resistor of resistance R as shown. After how many time constant is the charge on the capacitor is 1/4 of its initial value. See, they're just not asking you how many seconds. They just want to know how many time constant. So that's kind of no problem. Discharge, no big deal. This chart means the charge at any time starting from the maximum charge possible, and it's going to be exponential decay. Cool. Just use it. But then what you want is you want it down to be just 1/4 of the maximum. So this means you put the EC04 on the left-hand side. See? And then because you want everything under time constant, so we'll see at the end it's going to be simple. But now EC cancel. So what you get over here is 1/4 is e to the negative t over RC. Take log on both sides. Just do the inverse. So this log 1/4 is just negative log 4. And it's just negative t over RC. So that means t is just log 4 times RC. You guys with me? But RC is just time constant. So if you want to ask in terms of how many time constant, I would say log 4 time constant. And you are done.
Okay.
Does that make sense? So if you want to answer in second, you just take log 4 times RC. This is in second. But if you want in how many times constant, as you can imagine, you just divide the whole thing with the time constant. So this t cancel, you ended up with just log 4 time constant. You're done. And everyone say the same thing about this. So it doesn't matter what value of R, what value of C, as long as you're talking about this simple RC circuit, it's going to take you log 4 time constant for your charge to get this charge down to only 1/4 of the maximum value at all time.
Okay.
Nice. Okay, that's good. All right, one last thing, guys. Let's do one more, shall we? And this is going to be the question that I think that's make things a lot easier. All right, and well, I'm probably going to ask you this in the final because it's simple. Consider the circuits in the figure. Now they want to know the current through the battery after the switch is closed. That's the first question. And the second one, after a very long time. So they're doing the extreme cases. Okay, they don't do exponential, don't do anything. They just want to know what is going on at time 0 and what is going on at time infinity. So that means this is what you are trying to get to. Okay, and this is want to end this whole course with this simple example. We already talked about if you are the charge that enter the capacitor first, the capacitor will appear to you just like a blank room, even though you don't even feel like it's a room. It's just like an electrical wire. You feel like there's nothing against you at all. So that means what I can conclude is this: at time 0, your capacitor behave just like a straight wire. You guys with me here? Because you're not going to feel anything. You don't feel like this is a room. You don't feel like there is anybody in the room. So it's feel like you're just traveling in the wire without anything blocking you whatsoever. So that's what it is. However, if you wait until it's long time, so your capacitor has already been fully charged. So the room is already filled. It's full. So you cannot enter the room anymore. So that means your capacitor will behave like a broken wire because you do not allow to go in anymore. So you have to stop traveling. No currents flow. So it's a broken bridge. You won't allow to pass anymore. Does that make sense? So that's why I would like to conclude today's lecture and our course with this. So that means part A, you just treat your capacitor just like an electrical wire. So your circuit will look like this. Voila. With me? Yes. And part B, your circuit will look like this. That's it. Because this is broken. So when it's broken, that part of the circuit, you just ignore them. You don't need anything anymore. So your circuit will be reduced down to only just this part. We just, hey, don't care. I don't care about this. And from here, you can calculate your current very easily. But okay, then on this one, this you don't need any like Kirchhoff rule or anything. This one, you can just doing the equivalent resistance. So it's R over 2. So your current over here at time 0 is just going to be I equal to E over R. So that's it. You are done for the part A. And part B, I infinity is going to be E over R. And you are done.
Okay.
All right, guys. So, all right, I think I have one more, but this one you can try. It's the same kind of question. Okay, but maybe the circuit looks a little, no, not that bad. But overall, it's just these two extreme cases here. What happened at time 0? Your capacitor behaves just like a electrical wire, nothing at all. But when you wait long enough, the capacitor has been fully charged, so you do not allow to cross anymore. So your capacitor will behave like a broken wire. Okay. And we are officially done, guys.
Okay.
All right, guys. So thank you so much. And it's been a pleasure teaching you Physics 102. And I hope you guys have learned something, okay, or found physics to be lovable, I guess. All right, guys. Thank you so much. And I wish you well, and I hope you're doing well in exam and everything in your life. And good luck. And I will see you in our final exams. Yeah. Okay. Bye-bye.